The basics of probability. Or always means to add probabilities, and only means to multiply probabilities if n is greater than 1. Otherwise, and means intersection if n equals 1. So I highlight that the most important thing to consider early on in any probability question is how many things are going to be selected. That's going to dictate a lot. You'll see that as time goes on. Okay, so let's suppose we have this two-way table. We got seniors, we got freshmen who attend class regularly, infrequently, or they can't find the classroom. Look at that, 10 freshmen. Okay, so we got these marginal distributions here. What's the probability we randomly select one person and they're a regular class attendee? That's either here or here, so we add the two probabilities together. What's probably select one person, and that person is a senior and regular? Well, and means intersection. It means the person has to fulfill both of these requirements or both of these descriptors. So it's these 40 people who are both seniors and regular. Selected one thing, and means intersection, does not mean multiply. All right, then finally, what's probably get a senior or someone who's a regular attendee? The easiest thing to do with the two-way table is just go ahead and look at the different cells. These people are seniors, these are seniors, and these people attend regularly. So the people or the people that work in this descriptor are here, here, or here. So we add those together. We get 80 out of 100. This week the teachers get 2 new markers. It's awesome. It's a big week. This week there's 8 red markers, 7 blue, and 5 green. Last week there were orange markers. Those things are awesome. But you know, red, blue, green, not bad. We don't get new cars or anything, but we get new markers. It's fabulous. Who's complaining? Anyways, so I'm the first one, suppose, that gets the markers first, and it is possible to get duplicate colors. So here we go. What's the probability of a person getting a blue and then a green marker? We see the word and we're going to be selecting 2 things, so and means multiply, and we know we're going to be selecting without replacement because I get to end up with 2 markers. I don't have to put the first one back. So at any rate, what we have is probably the first marker is blue, is going to be 7 of the blue markers out of 20 altogether. And means multiply because we're selecting 2 things. And then probably the next one is green. There are 5 green markers out of 19 markers that are left. That's going to be our probability. What's the likelihood that both markers are the same color? Now, you could make a tree diagram. It's nice to do things visually. It's not a bad way to go, although I will say that if you get too many things selected, tree diagrams can get pretty ugly. But this is a nice way of displaying things. And by the way, Venn diagrams are used when you're selecting one thing, and tree diagrams are used when you're selecting 2 or more things. So know when to say Venn, and now is not the time. We should go tree diagram with this. So what we can do is we could get a red on the first selection, and then a red on the second one. So we'd multiply these 2 together because we're selecting 2 things, and means multiply. Or, we would add to that, we could get a blue on the first selection and have a blue on the second one, multiply those 2 probabilities together, or add this final scenario, we could get a green and a green. So the tree diagram will show us what to do, and then we can write in the probabilities on there. But I would prefer, honestly, if students could get to the point where we would just rephrase some of these questions using the word and or. And because we're selecting 2 things, more than one thing, and means multiply and or means add. So it's a roadmap. It really makes things, I think, quite easy. In this problem, what's probably getting 2 the same color? Well, rephrase that. That means you could get a red and a red, or a blue and a blue, or a green and a green. And means multiply, 2 things are selected, or means add, there you go. You just do that work right there. In this Venn diagram, now, when we're selecting one thing, we should go to a Venn. So let's suppose A would be seniors, B would be students that are in extracurriculars. So these people would be in extracurriculars, but they're not seniors. These people are neither seniors nor in extracurriculars, so we make sense out of the Venn diagram. Here's our 2 probabilities right here. Now, if we were asked to find the probability we get a senior and a person involved in extracurriculars, likely the problem is not asking us that we're going to get a senior, then put that name back, and then select again and get a person involved in extracurriculars. If that was the case, we'd be selecting 2 people, and would be to multiply. But if we're looking at a Venn diagram, we should be selecting just one person. So in this case, the word and would be intersection. So you look at the Venn diagram, are the people who fall into both descriptors, they're seniors and they're involved in extracurriculars. That would be the 10% in the intersection. So and means intersection, we're only selecting one thing. Two events can be mutually exclusive or they can be independent. So if you recall, if two events are independent, you get the intersection by multiplying the probabilities together. There's ways to explain that. We're not going to do that right now. Memorize it if you have to. Then dependent events would be two events that have an intersection, they have an overlap, but any probability can go in here except what you get when you multiply the two probabilities together. In the previous Venn diagram, that was not independent. These are not two independent events, because if they were independent, we would take this probability times this one, which is 0.08. We would need to have a 0.08 chance of both events happening simultaneously. That's not what we see in the intersection. Therefore, these two events are not independent. And that's the most common test for independence. See if what you find in regards to the probability of the intersection is what you get when you multiply the two probabilities together. So if we go to this problem here, we'll also remember this formula, the addition rule. Add the two this means or, so what's probably that A or B happens if you're selecting one thing? It's probability of A plus B minus the intersection. We'll see why that is. So if these are the two probabilities, we say what's the probability of A or B happening if the two events are mutually exclusive? If they're mutually exclusive, they have no overlap. And so it would be the probability of A, which is 0.4, plus the probability of B, which is 0.5, minus nothing, because there's nothing in the intersection. So our probability would be 0.9. These are the easy ones. But what's the probability of A or B happening if the events are independent? We have a little work to do. We have to remember what it means for the events to be independent, and what goes in the intersection then is what we get when we multiply the two probabilities together. So 0.4 times 0.5 is 0.2, that goes in the intersection, and altogether A is made up of these two sections, so altogether A's probability is 0.4, altogether B's probability is 0.3. If you just want to look at the Venn diagram, you can say, hey, A or B happens here or here or here, so the probability would be 0.7. But you can also go to the formula and say, well, probability of A is 0.4, probability of B is 0.5. The reason you would have to subtract the intersection is because it gets counted twice. Oh, no, please. There you go. All right. So the 0.2 gets counted twice. It gets counted in A when we add these two together to get the 0.4, and it gets counted in B when we add the two together to get 0.5. That's why the formula has you subtracting it out. So whether it's the formula or the visual inspection, you get 0.7 for your probability of A or B happening. All right, now are A and B independent events if these things are true? And there's two ways we can go with this. We can go the formula approach and solve for the probability of B, because ultimately the test we're going to run is is it true that the probability of the intersection is going to equal what you get when you multiply the two probabilities together? I like putting a question mark above the equal sign to say, is it true that this probability equals the product of those two probabilities? So we could get the information about the probability of B from the formula if we plug in everything we know into the addition rule. So if we plug in everything we know and we solve for x, we get that x is equal to 0.38. So down here we say, well, we know that what was in the intersection was 0.18. So is that what you get when you multiply the two probabilities together? Negatory, we get 0.228, so therefore we know that the two events are not independent. I think it's probably easier just to go to the Venn diagram and say, okay, we know this, and we know all together the probability of A or B happening is 0.8. So we add these two guys together, and that gets us 0.6. We need to take it up to 0.8, so this must be 0.2, so that these three probabilities add up to a total of 0.8. So then real quickly we can say, well, all together then the probability of B are these two sections here. They add up to 0.38. And now again, we put that into that test to see if the two events are independent. And again, we fail the test, so we conclude A and B are not independent events. Let's go back to this situation where we have the markers. let's say we're going to randomly select 4 markers and we want to find the probability that all the markers are red. Well, we can rephrase using and or, so we have, on the first try, we'd have an 8 out of 20 chance of getting a red marker, and on the next selection there'd be 7 markers left out of 19, and then there'd be 6 out of 18, and then there would be 5 out of 17. Multiply together, and that gives us the probability that they're all red. Now recall that when we need the probability of at least one red, it's easiest to use the complement rule. So what that is that this, anytime we see the words at least one, we should say we can save time by doing 1 minus the probability of the complement, which is that we get no reds. And the only way we could get no red, if you look at the tree diagram, is on the first selection you don't get a red, and then you don't get a red, and you don't get a red, and you don't get a red. So it'd be 1 minus, probably the first one's not red. If there's 8 red out of 20, it means that there's 12 markers. Nice. It means that there are 12 markers out of the 20 that are not red. And then what's left on the second choice is 11 out of 19, then 10 out of 18, and then 9 out of 17. Now I might have gone through that a little quick, so let me just say this. The reason that when we see the words find the probability of at least one red occurring, the reason we go to the complement and find the probability that we get no reds and then do 1 minus that can easily be seen by the tree diagram. If we're going to find the probability of getting at least one red directly, then life becomes fairly miserable, because we can get a red if we get a red and then a red and a red, a red, or if we get a red marker, then a black, or I'm sorry, then not a red marker, and then a red marker and a red marker. If you basically look at all the scenarios on the tree diagram, there's really 16, 2 to the 4th power, 2 decisions, 2 outcomes on each level, 4 levels. So there's 2 to the 4th power outcomes. There's 16 different ways that you can end up with 4 markers that are individually either red or not red. And if you look at all of those 16 ways, all of the ways that incur getting at least one red, it's this one, this one, this one, this one. It's 15 out of the 16 scenarios will cause you to get at least one red marker. So if you find this probability directly and you rephrase using and or, you're going to say, well, I could get a red and a red and a red and a red. Or I'm going to add to that a red and a red and a red and not a red. Or add to that whatever. So that's why the time saver is when you see the words at least one in probability, you say, no, I'm not going to do that directly. That's working too hard. I live in the States. We don't work, we do, but we find shortcuts. Anyway, so we do 1 minus the probability that we get no red markers, because the only way that you can't get a red marker is if all 4 selections left you with no red marker. So if you find that probability, the one thing you do know is that when you add up these 16 probabilities, you must cover 100% of everything that can happen. So all of these add up to 100% or 1. So if we do 1 minus the only scenario that leaves us with no red markers, by default, what's left is the probability that we get at least one red marker, which happens in any of those 15 scenarios. So bottom line, memorize it if you have to. When you see the words find the probability of getting at least one, find the probability of getting none of those successes, and then do 1 minus that. So the basics of probability, what do they lead into? They lead into conditional probability, binomial probability, geometric, proportions, normal probabilities, sampling distributions, confidence intervals, p-values, type 1, type 2 error, and expected value, one of the most important things in all the world of statistics. So understanding the basics is vital for us to be able to do the rest of these, and there's more videos on some of the rest of these topics.